Swayam Prabha. Digital India. Educated India.
Is minus mu dot H, scalar product. H is a magnetic field vector. So you go to the laboratory further down sometime during this course. There is a laboratory called the Nuclear Magnetic Resonance Laboratory. Okay, you will see that sometimes. Let me see. Yeah, I guess you'll see superconducting coils. The superconducting coils actually create a magnetic field, very steady magnetic field. And these are very high magnetic fields, not 5 Gauss, 10 Gauss like the Earth's magnetic field and so on. These are probably 30,000 Gauss or maybe 20,000 Gauss. Okay, 10,000, sorry, 200,000 Gauss, 20 Tesla. 1 Tesla is 10,000 Gauss. Very strong magnetic fields. And in this magnetic field, the nuclear magnetic moment interact with the magnetic field by this project, this equation, the dipole moment. Now, you can see that if this is the angular momentum, spin angular momentum of the electron, for example, causes this, obviously spin angular momentum in the magnetic field has two possibilities. Either towards the magnetic field it is aligned or against the magnetic field it is aligned. Therefore, what happens to the magnetic moment? This also can be aligned towards the field or against the field. If it is aligned towards the field, mu dot H cos theta, mu times H times cos theta. I remember the formula for the vector scalar product. Therefore, it is mu times H times cos theta. So, if I say that this is the mu and this is theta, okay, then the interaction is mu dot H. Now, which one of this is stable? Which one of these two is stable in the magnetic field? It's like the North Pole pointing towards the North Pole, the South Pole pointing towards the South Pole in a compass. Okay? So what you have is, this is stabler. A stable system has negative energies. Therefore, if theta is 0, for example, it's perfectly aligned along this direction, theta is 0, cos theta is 1. So now the energy is minus mu H, lower energy for the system. For a spin plus a half, if it is a nuclear, for example, proton, if the system has a plus a half spin, okay, H bar, you see that the orientation is stabler. The minus a half orientation is less stable. Therefore, the moment you put a magnetic field, you see you are creating what are called two energy levels for the proton. Some protons may be up here, some protons may be down, but how many will be up, how many will be down? There are formulas to calculate. Okay? More number will be up, less number will be down, or more number will be down, less number will be up at any given temperature. What is stable system? Obviously, more number should be aligned with the field so that it's stable. Less number towards against the field. But what is the difference between more and less? 1 in a million. If you take a million molecules or million proton atoms, 500,000 protons up, 500,000 protons down means it's fine, there are no magnetic properties. But if 499,000 is up and 499,999 down and 590,001 up. So only one spin makes a difference to get a magnetic moment for the system. Because if more are pointing in one direction and less are pointing in the other direction, there is a net magnetic direction. Okay, so the net magnetic direction is 1 in 500,000. But we don't have 500,000 protons. We have, in a small sample in the lab, we have usually 10 raised to 20 protons. So that's how many millions? 15 followed by 14 zeros, right? 10 followed by how many zeros? 14 zeros million, right? 10 raised to 20 number of atoms. Therefore, you have a huge number of protons, and so reasonably large number of protons are up. Yes, little less number of protons are down. So the system gets magnetized. The moment you put proton in a magnetic field, you put a larger number of protons in the magnetic field, the system gets magnetized over a period of time. And now also the system gets two energy levels. The lower energy level, this one, and then the higher energy level, which is this one. Now what you can do is, you can now play around with the protons by adding a radio frequency field that will excite the protons from the lower field to the higher field by shining that magnetic, these are all magnetic energy levels. Therefore, you must put in an oscillating magnetic field. Oscillating magnetic field whose frequency matches this gap. You can see now you can play around with the protons moving from lower energy to upper energy and then creating the cycle. That exactly is called proton nuclear magnetic resonance. That's the fundamental process, and the first time it was observed successfully was in 1946 and 1947, around that period, by two people. Okay? Two physicists observed that. Before that, several experiments were done, but they did not measure this, they failed. And those failures eventually led these two people to come up with the right model. And the two people who discovered this resonance using the energy, let's call this as E minus, and we call this as E plus. Plus is the plus orientation, plus a half. So plus is lower in energy, and the minus is higher in energy. And the radiation that matches the gap is called the oscillating radio frequency. The frequency is radio frequency. Oscillating radio frequency. Because the energy levels are very, very small. Very low energies. The gap between them corresponds to radio frequency energy range. Therefore, the nuclear magnetic resonance was discovered by two people, Felix Bloch and his team, Felix Bloch plus his team members, and Edward Purcell and his team member. Two people. They both won the Nobel Prize in 1952 for the discovery of nuclear magnetic resonance. Okay. So, a little bit of mathematics. Okay. We will write them down. So, the nuclei, because of the magnetic, the quantum number, they have an angular momentum J, and the angular momentum J times gamma gives you the magnetic moment for the nucleus, and the interaction of the magnetic moment with the external field, if you call this external field as the z direction of the laboratory, okay, then this is the magnitude of the external field. The magnitude of the external field, this is z direction, therefore this will interact only with the z component of mu, not the x and y component, because they are perpendicular, so they cancel off. So what you have is minus gamma, okay, the j is actually, I should write gamma h bar I, where I is the angular momentum vector without dimension. Angular momentum has the dimensions of h or h bar. H bar is h by 2 pi. Okay, so this is called the dimensioned angular momentum J, but this is gamma h bar I, where I has two orientations in the field, namely if this is the z direction, h naught times z, then this is Iz is equal to plus a half, and this is plus a half is this. Iz is equal to minus a half, which is that, okay, equal. So these two energies give you the minus mu dot h will give you minus mu, h is h naught z mu dot, okay, and you can write the mu as gamma h bar I. So you have minus gamma h bar. Now h naught, which is a constant magnetic field. So the mu now interacts only with the z, which means it will only have the z component of mu that will be picked up by this z, and that is I z. Okay. So this is the energy in the magnetic field. Okay, any questions till now? Is everything okay? Yeah, tell me. No, what I said was Iz plus a half is the orientation towards the magnetic field. So that's a lower energy. And the value of Iz is plus 1/2. Okay? The projection. The projection of Iz onto the magnetic field direction is a plus a half. Actually, the magnetic moment will not align exactly with the axis. It will be aligned at an angle theta. We'll see that later. But so it is a plus a half. And the other one is called the minus a half. Therefore, you have two energies. If the Iz is plus a half, you have one. Yeah, you can see that right away. So you have E plus is plus 1/2, right? E plus is minus gamma h bar h naught. Iz is 1/2 by 2. Okay. This one has a plus half value towards the direction, and the other minus is plus gamma h bar h naught by 2, because Iz is minus a half. So you have two energy levels, the lower energy level, this one, and the upper energy level, this one. Okay. So what's the gap between them? The gap between them is gamma h bar. Delta E is gamma h bar h naught. Okay. Gamma h naught has a special name in honor of a physicist, and this is called the Larmor frequency. Joseph Larmor was one who studied magnets for quite some time. So the gamma h naught is called the Larmor frequency, and you can see that this is angular frequency. Please remember, h is h by 2 pi. Okay. Therefore, if this whole thing has to be energy, this has to be 2 pi times some nu. Right? Otherwise, this is an angular frequency. So we write this as h bar omega naught, which is the same thing as h nu naught if you remember h bar is h by 2 pi and omega naught is 2 pi times mu naught. So now all you need to do is to find a radio frequency field whose magnitude is this, to excite the nuclei from lower to upper, upper to lower, lower to upper, and so on. Okay? So that is the resonance that we cause, and this resonance was seen as an induction, magnetic induction in the coil that was used to measure the experiment, to do the experiment. And the first time that was done was by Felix Bloch, and immediately around that time, Edward Purcell also discovered this, and Felix Bloch was in Stanford University. Felix Bloch was in Stanford University, and Purcell was in Harvard University. Two big names. They contributed to the discovery of the magnetic moment, and the magnetic resonance. Earlier, people thought that the magnetic moment is due to electric charges in the system. Electron has a magnetic moment because it is a spinning electric charge. Proton has a magnetic moment because it is a positively charged nucleus. It came as a big surprise later when somebody found that neutron has a magnetic moment, okay, also plus a half. So then the question is very clear, what is the origin of the spin? It's not just a charge or anything. To understand the spin, one must study a field called quantum electrodynamics, which was very beautifully developed by three people, Julian Schwinger, Sinitra Tominaga, and then Richard Feynman, three people. They won the Nobel Prize for the quantum electrodynamics. You need to understand quantum electrodynamics to appreciate the origin of the electrons, the origin of the spin half system, spin quantum numbers. Therefore, it's not just the electricity or rotating electric field that generates a magnetic field, but this is fundamental to the molecular nature, and one uses this as an example to say that all things need not have a physical explanation. Understandable, geometrically, pictorial representation. Spin is anything but pictorial, but spin is a real property of the system. And what we need to do is that in the absence of our understanding of what spin is, we can do what all the commerce people do. They don't know how the money is generated, but they know how to make more money out of it. So now that you have a handle that somebody discovered that a transition can happen between the two new states of the electron or the proton, and therefore you can oscillate between them. The next question was, how do we use this in chemistry, or how do we make use of this? Fine, this is a nucleus which has a spin a half. Now, what is interesting was, immediately after this was discovered, somebody tried to take the proton magnetic resonance spectrum of this molecule. There are how many? Not one proton. There are 6 protons here. So one thought that you will get the proton magnetic resonance spectrum quite clearly. But what is surprising is that they didn't get one absorption line. Please remember, if the energy absorbs from E plus to E minus, there is an absorption in line. This is a spectral line. You are all familiar with that. This is the amplitude, and this is the frequency nu naught, and this nu naught corresponds exactly to this nu naught. Okay? Exactly this nu naught, there will be a frequency, that is absorption. Okay? It's not a straight line, it's actually a line width, but yeah.
So, would you want to repeat the name of gamma H naught you told us?
What is the? Cosmic rays.
So, no, gamma H naught, you said it was something.
No, gamma is a gyromagnetic ratio. It's a property of the nucleus.
So, in the formula, delta E is equal to gamma H bar.
Yeah, that gamma.
So, not the gamma. You told that gamma.
Which one is? Delta E is the magnetic energy gap. Come again?
The Larmor frequency, I didn't get that.
Larmor frequency. That is gamma H naught.
Yes, sir.
Yeah, it's over there somewhere. Did I write that here? Oh, I erased it? Okay. Gamma H naught is known as Larmor frequency. Joseph Larmor frequency, L, capital L. Okay. Now, what is interesting is that when the spectrum of, what is this? This is ethanol. So, if there is a proton magnetic resonance, and if all the protons have the same magnetic field, you should get only one line. They got 3 lines. Okay? They got 3 lines. And if you do, people who did this experiment, and if you do a little more carefully, each of these lines itself was further split into smaller lines. So, proton magnetic resonance, apparently when you plotted it against nu naught and the frequency, You get one line here, another line here, and another line here. Why is that? It's very simple. What is the gamma H naught? Gamma H naught is the Larmor frequency of the proton corresponding to H naught. H naught is the external field, magnetic field. So for all these times we were looking at the nuclei, but these chemists decided that the electrons also have magnetic moments, right? Therefore, the electrons around the nuclei generate small magnetic fields. That magnetic field offsets this magnetic field. Okay? It may add to the magnetic field or it may subtract the external magnetic field. It's like a shield for the external magnetic field. Now, how much of it will happen? If there are more electrons around the hydrogen, the shielding will be stronger because more magnetic, local magnetic field will protect it from the external field. If there are, you remember, this hydrogen has the least electron density because the oxygen pulls all the electrons out closer to itself. Therefore, this proton is near bare proton. So it sees all the external field. Whatever magnetic field that you apply, it sees all of that. This proton is a little this way, that way. You know, it's close to the oxygen, but it's not bonded to the oxygen. Therefore, this proton has magnetic fields which are smaller than the magnetic field of the electrons here. Therefore, this proton sees, if this sees all H naught, this sees some H naught, and it sees some less H naught. Okay? Therefore, each proton sees a different magnetic field because its chemical surroundings make sure that the electron density compensates for some of the external magnetic field. Now, this is chemistry because now the connectivity between the different proton groups and the fact that the electron density plays a role suddenly brings a very inert experiment like, one transition between your proton two energy levels. Now suddenly it brings you three transitions because these three protons see three different magnetic fields. These three protons are shielded differently by their electrons. This is least shielded, this is somewhat shielded, this is the most shielded. Now, please remember, your absorption frequency is only h nu naught. Your coil, radio frequency coil that generates, it generates only nu naught. Therefore, this nu naught cannot result in simultaneous absorption of all three of them. Okay. This has to match with one of the resonance frequencies. Then that proton will absorb that. But please remember, if this frequency matches with this hydrogen, then only this hydrogen will absorb. But the moment this is due to gamma H naught, the nu naught is due to the gamma H naught, magnetic field. Therefore, you keep this constant, but now slowly change the magnetic field. At one magnetic field, this will be absorbed. At an increased magnetic field, you see, eventually this energy range will be matched by this proton because you have increased the magnetic field. So this will absorb. Increasing magnetic field. And therefore, what is this one? Which proton is this one? OH proton. Because that has all the field removed, electron field is removed, most of it is removed. Therefore, it sees almost everything that is as an external magnetic field. Therefore, it is closer to this H naught, the earliest. But then this proton requires even more magnetic field because the shielding is higher. Otherwise, this energy gap will not be matched. Therefore, you see that you fix the radio frequency coil for absorption as one frequency, you have to change the magnetic field for absorbing energies by each of these protons, and this will be CH2, this will be CH3. It's very interesting because in the very first experiment that Felix Bloch did with his assistant, okay, Felix Bloch had Bloch, Hansen, and Packard. These were the three people who published that paper. I think it is Hansen, if I remember, or Packard. I don't remember now. Felix Bloch was trying to absorb the resonance frequency for water molecule. Yes, yeah, go ahead.
Sir, wouldn't the size of the peaks be different based on the...
No. Size is arbitrary. I'll tell you later. Yeah, right now I'm just giving you an arbitrary process, okay? Incidentally, even arbitrarily, I think I did it right. This is slightly more, this is slightly less, okay, if you want to. And I'll tell you why. 1, 2, 3, okay, later. The intensities are dependent on the total number of protons which absorb at that frequency. Yeah.
So you initially said that instead of one line that observed, and each line had each line corresponding
No,
to...
you keep varying the magnetic field.
Yes, so you said that each
Each proton will have two energy levels.
Okay.
That gap energy level depends on the magnetic field. So if the proton is shielded, the external magnetic field will not be seen, the gap will be small. Therefore, you have to increase the external magnetic field in order to match that gap of h nu naught. So it is like this, the proton of the OH sees the nu naught first because it sees all the magnetic field. Therefore, the magnetic field matches nu naught right away. But then the second proton does not see all the magnetic field. Whatever that is, it sees less of it. So now you have to increase the magnetic field to make sure that it is nu naught. And the third one sees even less because it's most shielded. And therefore you see that you have to increase the field even further. That is why the direction of increasing the field tells you which proton gets first resonance, which proton sees the second resonance, which proton sees the third resonance. Okay, it's clear? Yeah. So now chemistry has come into play because now molecular structure has details in NMR spectroscopy which Bloch and Hansen did not think about. Okay, they saw proton spin and proton energy levels and they came up with a resonance phenomenon. Chemists now started skillfully exploiting this to study the structure of the molecules. Okay, now you see that these three protons have three different energies, magnetic field. The original experiment of Felix Bloch, he said, yeah, go ahead.
Sir, why is it that the electron's magnetic field will only subtract from H naught?
What is the electron?
The electron's magnetic field,
Yeah.
why must it only subtract from H naught?
No, the electron has a negative charge, proton to electron negative charge. Therefore, the electron magnetic field sort of blocks the external magnetic field due to the opposite sign.
Yes, sir.
Okay? Yeah. You got it? Therefore, the electron always shields the nuclei. Okay? Most of the nuclei do. Okay? So, Felix Bloch set up the parameter, some magnetic field, and he turned on the coil, radio frequency field, no absorption, no resonance frequency. So, he kept repeating this experiment for many days and nothing was seen. Earlier magnetic resonance experiments had failed. There were reports published in journals that the failure to detect nuclear magnetic resonance has been published. So, Felix Bloch probably believed that something is wrong with this whole exercise. But his assistant, anyway, the story is mine, okay, it's not exactly the story of what it was. His assistant on a Friday evening, I'm told, okay, decided that, okay, we are not getting any results, close the whole thing, we'll go home or we'll go to some place, have some drink, okay. So, Friday evening, what is called you are not supposed to know, okay, you are all below 18. So, Friday evening, it's happy hour beer is half priced. So, people go to the pub in the happy hour period They can take 2 beers for the same price, 1 beer price. But the other hours you get many more. Okay, these are all my stories. Okay. Point is that they went away. But before going away, Hansen or Packard, I think it is Hansen if I remember, he switched off the magnetic field because the lab has to be closed. He switched off the magnetic field and the oscilloscope, which was like this on the screen, okay. As he switched off the magnetic field and was about to leave, he saw something like this, blip, okay. Actually, the blip is like this, like that, okay. It won't come this way, come this way, okay. He was very carefully watching as he turned down the magnetic field. See, when you turn off the magnetic field doesn't go to 0 immediately. It goes slowly to 0. It takes some time. He saw a blip. He said, that's interesting. We were trying to see some signal, but there is a blip here. So after the field came down to 0, he turned on the magnetic field. Okay. And then as the magnetic field was increasing, the blip appeared and then disappeared. The magnetic field changed its amount. Eventually settled down to what they set up in the beginning. So he said, this is to be seen. He did that several times. Turn off, turn on. And there Professor Felix Bloch is waiting for his assistant to join him. He says, what's happening? He says, Professor, wait, there is something interesting, I'll tell you. Okay. So he sees that the blip comes in when you turn off the magnetic field. The blip comes out when you turn off the magnetic field. And again it happens. And then he said this to Felix Bloch, sir, this is what is happening. You were looking for a signal, but you didn't get the signal, but the signal seems to appear in some other magnetic field. So Felix Bloch thought about it and said, okay, I'll go back and redo my calculations. Tomorrow, come, Saturday, but it's all right. Tomorrow we'll come and see this. It's important. So he went home, did the calculations, he checked again, and he found that there was a small error in the magnetic field that he calculated. When he recalculated and set the magnetic field, that happened to be the exact field at this point. Okay? And so they saw the signal. And with that, they also got the Nobel Prize. Okay? That's how it happens. Nobel Prize happens if you are not just smart, you have to be very observant and you have to be also thinking about observations that don't match your expectations. Why are we getting this? What is wrong with that? So the idea is that you can see that the resonance frequencies happen at different magnetic fields for the same nucleus if nu naught is fixed. Can you do this experiment in a different way instead of doing this? What about I keep the magnetic field fixed, but I change the absorption frequency of the coil. I change it from lower frequency to higher frequency by a turn on. Can I do that? Because the magnetic field is fixed. Therefore, each nucleus will have a different magnetic field, different absorption frequencies. The H nu for that nucleus will be different from the H nu for this nucleus, for that nucleus. But now if I apply radio frequency field changing, I will also observe the same phenomenon. So, if I put this, instead of increasing magnetic field, if I put this as increasing radio frequency field, which one will I see first? I will see CH3 first, and I will see CH2 later. I'll see OH later. Okay? You see that? Experiments can be done both ways. But today, the experiments are done using fixed coil, and the magnetic resonance spectrometers are named after the frequencies of the proton absorption frequency. Okay. They are called 100 megahertz NMR spectrometers, 100 megahertz NMR spectrometer, and 300, 500, 700, and I guess today we have 1200 megahertz. Experimentally we have these different spectrometers. This one costs probably about 25 lakhs. This one costs about 3 crores. And this one costs about 12 to 14 crores. If you want to buy that machine. Because increasing magnetic field, having much higher steady magnetic field, the electronics requirement and the technology requirements are very, very tight. And therefore, such equipments cost a lot. What we have in our lab is, we have two of them, one 400 megahertz spectrometer and another one 500 megahertz NMR spectrometer. The 500-400 refers to the nu naught for proton, free proton. That is proton from which all the electron has been removed, bare proton. It's called the bare proton. Okay. That is this one. Now this is for proton. So we will stop here, have a break for about 10 minutes, and then we'll come back and complete this experiment. What happens if instead of proton, we have other nuclei like nuclei which have spins, not only proton, but maybe every nucleus, something or the other. An isotope or the other has an integral burst of spin quantum number, and therefore you will see many nuclei that can be measured. And the most famous example after proton is carbon-13 isotope. That is 6 protons and 7 neutrons, carbon-13. Carbon-12 does not have a spin quantum number. Okay? Therefore, most of natural carbon is not measurable in NMR spectrometer. You have to do isotopic enrichment. You know, carbon-13 naturally is about less than 1% or maybe 1.4% of the natural abundance. Therefore, you have to make carbon-13 rich, and you can do carbon-13 NMR spectroscopy. You can do fluorine-19 spectroscopy, so many other nuclei. We'll do that after we take a break, okay? But this is the fundamental experiment. Yeah. Yeah, it's a break now. So those of you who want to ask questions, stay. Yeah.
So could you just repeat how the graph reverses when we take the x-axis as increasing radio field instead of magnetic field?
Yeah. What happens is, if the magnetic field is fixed, which proton will see the minimum magnetic field?
The one that's
most shielded. Therefore, as you increase the frequency in the axis, will that be the first one to be observed? That will be the first one to absorb the energy. So the next proton will be what? The CH2 proton. Its frequency will be higher because the magnetic field is fixed.
Because it's less shielded compared to the...
That's right. Therefore, the magnetic absorption frequency will be more. So it will be seen the second time. And then the third. Therefore, it's the opposite. As you increase. Okay. CH3 comes first, CH2 comes next, and OH comes. Okay. Yeah. Because OH sees all the field. Okay. Therefore, its frequency is the maximum. The frequency is proportional to the field, seen by the nucleus. If the frequency is all the field, then its energy gap is the largest. If the frequency is less than all the field, the energy gap is smaller. If the frequency is the least of all the field, the energy gap is the smallest. So this is the first one as you increase the radio frequency. This is the first one, then the next one, and then the next one. So it's the opposite. Okay? Yeah. Okay. I need about 5-10 minutes. Yeah, go ahead. Yeah.
So, you explained about the dipoles of the
Yeah.
carbon dioxide molecule. So, it has different orientations of the dipole, and how would we know which method of
What different orientation? Carbon dioxide?
the
Oh, you mean the-
asymmetric one and the bent?
Oh, no. The molecule, it's like, now, the best example is you have a piano or violin. It has all the frequencies built in. Which key you press gives you that corresponding frequency. The molecules in free space are vibrating randomly. They are a mixture of all these individual motions. So it is not that some molecules are like this, some molecules are undergoing this. No. The molecular motion is complex because all these harmonic oscillators are interacting with each other. However, the moment you press a key, what do? You are selecting a frequency in the piano. So you get only that sound. So what happens is, if now you shine radiation that corresponds to the oscillation frequency of the bending motion, the moment that energy is seen, molecules recognize this energy can be absorbed by me. And therefore, molecules show the bending frequency by absorbing that resonance, by absorbing that radiation. But if you change that radiation to the next one, the molecules which are undergoing complex motion, they see that I have a frequency which is natural to me, asymmetric, the stretch. So by the time this frequency reaches that asymmetric stretch, molecules start absorbing to undergo excite motion of the absorbing, that stretching frequency. Likewise for the symmetric stretch. So the frequency selects which of the normal modes will absorb the frequency. Okay? So the process is selecting that frequency, but molecular motion cannot be individually visualized as motion due to this mode or motion due to this mode or motion. Because at thermal energy, kT, all the four molecular modes, vibration, are possible by the same molecule. Therefore, it looks in some complex fashion. The moment you select, it's like you put all the piano keys put together, you get what? You get one jarring frequency. You don't get a single frequency. Molecules are in that motion, all the jarring frequencies. But then you pick one key, you are selecting the molecules which will absorb this energy. That's what it is. Increasing? No. The field, electromagnetic field, has many frequencies. So the radio frequency field has the lowest frequency because it's a meter, radio waves. Radio waves are 100 meter waves, 1 meter waves. These days you don't play radio, but I used to play wall radios and so on. So we will do short wave radio, we'll do long wave radio, medium wave radio. The radio wave frequency means that the wavelength is 100 meters. One wave length is 100 meters. Therefore, its frequency is C by 100, which is the smallest. If the frequency is the small, the energy is h nu, h times the frequency. Therefore, the energy of a radio wave photon is the smallest. The energy of the cosmic ray photon, which is on the other side, cosmic rays are the shortest wavelength, 10 to the minus 20 centimeters, something like that, inward centimeters, and therefore they have the highest frequency. Therefore, the energy of the photon for a cosmic photon, ray photon, is much higher. That's what I was saying. So you go from radio wave, then the higher one is microwave. This CH3, CH2. Okay, come over here. Okay. OH. Okay. So what happens is this proton sees much less than H naught actual. Okay. Therefore, its frequency is proportional to gamma H naught.
Because it's shielded and
Shielded. Yeah, because the proton is shielded by the electrons, the magnetic field seen by this proton for this external magnetic field, H naught actual, okay, this field is very small. Therefore, its absorption frequency is low because the absorption frequency is gamma times H naught. Whereas this one, gamma times H naught, it's higher compared to this. This is even higher because it sees all the magnetic field. Therefore, when you have a fixed frequency, you will see that the radiation has only one frequency, nu naught. But the magnetic field has to go up from here to here to here. This is the largest magnetic field you need because this number is constant. This number is only equal to this number or even before that. So this number will be seen by this nucleus first. But for this nucleus, the H naught that you see is not this gamma H naught, it's less than the H naught. So you have to increase the field. The frequency of the radio coil, the coil is fixed, okay? There is basically a, what do you call? You have a radio frequency coil. So this always generates, say, for example, 100 megahertz. Okay? Now, it's always fixed. Which nuclei absorb 100 megahertz? Only when their energy gap is 100 megahertz. Which one will be, for the given magnetic field, close to that? This will be close to that. Suppose you put the magnetic field, this is a smaller magnetic field will get here to the 100 megahertz faster. This needs much higher magnetic field. This needs even more magnetic field because it's shielded. So, suppose this absorbs in 2 Tesla, 20,000 Tesla. 20,000 Tesla will not be seen by 20,000 here. This will be different because this number is 20,000 Tesla. It's fixed. Which one? This number is fixed as 20,000 equivalent, Tesla equivalent. The coil frequency, radio frequency. Once that is fixed, you see the one which has the maximum magnetic field will be absorbing first. Then if you increase the magnetic field, this will also come close to that number. And this come close to that number. Therefore, you see that when you increase the magnetic field, OH comes first, CH2 comes later, CH3 comes later. That's what it is.
The other way around.
Other way around, suppose you keep the H naught constant. Okay? Now, which will see all of H naught? This will see all of that. Okay? So now, if you put nu naught, okay, if it sees all of the H naught, this nu naught corresponding to this H naught is the largest compared to this. Therefore, which one will come first as you increase the nu naught? No, as you increase the nu naught, this will come first because this has the lowest magnetic field. Therefore, this will come first. And then this will come.
Magnetic field and frequency are different.
Exactly. Gamma H naught is 2 pi nu naught.
Sir,
Okay, nu naught is proportional to H naught. Yeah.
is gamma a constant?
This gamma is a constant for the nucleus. Yeah.
So if we vary H naught, won't nu naught also vary? So
Nu
how
naught
can-
doesn't